And now completely opposite from discrete random variable. Continuous random variable. A continuous random variable has an unlimited number of values. And unlimited here, formally speaking, in many textbooks, it has the word being used is infinite or infinitely many. So we have an unlimited number of values or an infinite number of values. So let me point out a couple of quick examples right here. So a lot of time we measure, or think about in medical facilities, they measure the height of a person, or in general, the height. And this variable, once defined, it has an unlimited number of values right here. So someone can be as tall as 5 feet. Someone can be as tall as 6 feet. Someone can be as tall as 7 feet. But really, it's just our human mind that a lot of time we are tied down to whole values. But really, measuring device can go a lot more precise than this. So in between 5 feet and 6 feet right here, somebody can be as tall as 5.1 feet. Somebody can be as tall as 5.5 feet. And in between these two values, somebody can be as tall as 5.05. So it all depends on the measuring device, how precise the measuring device can be. But I'm trying to point out here is that once we define this random variable right here for x representing height of a person, doesn't have to be man, doesn't have to be woman, it doesn't even have to be adult. It could be just newly born baby. It has a length. And so this random variable has an infinite or has an unlimited number of values right there, indicating that literally speaking, there are all kinds of values out there. No, don't get me wrong that I'm not talking about how many human beings we have out there. Of course, the population for human being is still big for us to count, but here I'm talking about the kind of values that we can measure from the heights of human beings. So being tall, being short, and in between an interval of values, we have infinitely many different kinds of value between right here, theoretically and practically. And now to make our transition into continuous random variable from discrete random variable a lot more smoothly, then let's grow a comparison chart. So I'm going to create a 2-column table. One column on the left here is for the discrete random variable. The plan for now is we are going to summarize all the features we have seen back in the days we've been working with discrete random variable, and we're going to make a direct comparison with continuous random variable. And I'm sure we're going to be fascinated by all of these direct comparisons between the features of discrete random variable versus continuous random variable. And so, from what we already knew about discrete random variable, so let's summarize the idea of discrete random variables one more time right here, even though we're making our way into continuous random variable. But discrete random variable has, as the most important understanding about discrete random variable, is it has a limited number of values. And this is the biggest feature of discrete random variable. And from this important feature of discrete random variable, then it produces all the consequences that we're going to go through one by one. And so on the opposite side, continuous random variable has, any continuous random variable is having an unlimited number of values. And that's the main feature number one. And really, it's the biggest feature, being completely opposites from that same feature of discrete random variable. And any of these major differences here, being discrete, we got limited number of values. Being continuous random variable, we have unlimited number of values. And each one of these being in the opposite side, they're going to produce consequences. And so back to discrete random variable, as I said, it has a limited number of values. And so once again, allow me to briefly remind everybody about that example of the Wheel of Fortune again. All right. And so here it is. This was our Wheel of Fortune game that we brought up before as an example when we studied random variable. And so, and I did mention that this was a perfect example to illustrate the idea of having a discrete random variable, due to the fact that the nature of this game right here, as we define the random variable x to represent the outcome as money amount of each game, then in the way that is, then this game can only have a limited number of values. So anywhere outside of these listed values here, the probability to run into those values are going to be 0. And so, but now, due to that fact that about your discrete random variable is having a limited number of values, so now let's have even a closer look back into this example a couple more times right here. But so now if we pick any two values, say between $1,000 and $100 right here, so these two values have a, what I usually call, for a friendly term, I call it's a gap. Basically, it's just an interval, a difference. But think about it, this gap here will remain permanent. It's just the way it is for having a limited number of values. So between any two values here, there will be a permanent gap here. And more precisely speaking, I'm talking about once we arrange all the values of the discrete random variable in a certain order, let's say the decreasing order like this from top down, or increasing order from top down, or whatsoever, but adjacent value, that's what I meant right there. So adjacent value from the table will leave a permanent gap. So we're gonna have a gap between two adjacent values. And to be a little more precise than those gaps right here, basically we're gonna always have a gap between any two adjacent values. And so, as the bottom line, since discrete random variable major feature here, it's having a limited number of values. So consequently, as a consequence right here, it's always going to have a gap. There's a gap between any two adjacent values. And now, if we look over into continuous random variable, and as we already knew, continuous random variable, the biggest feature of it is that it has an unlimited number of values. And so think about that concept of having a permanent gap between two adjacent values. And I actually brought up that example, that quick demonstration example about a continuous random variable. So once again, let's say capital letter X is to be the random variable representing height of a person. And simply just the height of a person without any age restriction or anything like that. Then technically speaking, baby has a height too, and we got all kinds of height. And so I already point out, and I can point out again, but someone can be as tall as 5 feet. and someone can be as tall as 6 feet. But then in between, and I'm not talking, and here, not to mention, we still going to have more the height above 6 and a lot more height, other heights below 5. But let's just for now narrow our attention to within this interval between these two values. Then I also mentioned in our previous part of the video that someone can also be 5.5 feet. It all depends on how precise the measuring device can be. And somebody can be as tall as only 5.1 feet. Or somebody can be just simply 5.05 feet. So the question now for us is that when we're working in the world of continuous random variable, that concept about gap, does it really exist? And gap now, I mean, is there a permanent interval that exists between some two adjacent value? But hey, wait a minute. What two values can be regarded as adjacent? Is that 5 and 6 being adjacent? Or is that 5 and 5.5? So really completely opposite, and as being a consequence of unlimited number of values, then being completely opposite with discrete random variable. Here in continuous random variable, we really have no gap between any two values. And this concept, no gap, now I mean that truly there are infinitely many values between any two chosen values. And so now back into our main comparison chart here, where it precisely lists down the direct comparison between discrete random variable and continuous random variable. Then, as we now have learned and now summarize here, that the major difference between them is that discrete random variable has a limited number of values, and completely opposite from discrete random variable, continuous random variable has an unlimited number of values. And we already learned further that for discrete random variable, having a limited number of values consequently led to there's a gap between any two adjacent values. But then, if we're looking for that similar thing in continuous random variable, then we have to say, being completely opposite, having unlimited number of values for any continuous random variable, then consequently completely opposite from having a gap. Here for continuous random variable, we have no gap between any two values. And really, I also said earlier about having the concept of having no gap here is that it truly means it's equivalent to saying there are infinitely many values between any two chosen values. And then in discrete random variable, it's just the nature of the random variable itself right here, having a limited number of values. Then recall that we call the table like this table right here, we had a name for that. It's a probability distribution. And so what is in this probability distribution of our random variable x right here? So because and all due to the fact that we are having, out of this game right here, we will definitely have a limited number of values. So in the probability distribution for this random variable, we are able to list the values as a table. We can use a table, in other words, we can use a table to list all the values on one side and list the probability correspondingly on the opposite column, on the opposite side right here. Or as a bottom line, due to the fact that we're having a limited number of values, then the probability distribution precisely speaking, a probability distribution or any probability distribution of a random variable, of a discrete random variable, can be represented as a table. And that's important. We can use a table to list our probability distribution. We can use a table to represent our probability distribution. And now looking over into continuous random variable, let's look for that probability distribution. Let's find a way to construct that probability distribution. We must make clear that as long as we are looking at a random variable, then it must have a probability distribution. So a bottom line here I need to make clear is that any random variable must have a probability distribution. What matters now is that, and once again, let's stay with this perfect example for letting our random variable x to represent the height of a person. And so, and as we already knew, any random variable must have a probability distribution. But so let's try to build that similar table to represent our probability distribution here. Let's say x is to list out, on the x column is listing out, our table is listing out the values of the random variable. So somebody can be as tall as 5 feet, somebody can be as tall as 6 feet, and oops, somebody can be as tall as 5.5 feet, and somebody can be as tall as 5.1 feet, and somebody can be as tall as 5.01. So the question now is that when we are making our attempt to construct a table like this, where we're attempting to list down all values of the random variable, of our continuous random variable here, and then also making further attempts to track down the probabilities corresponding to each of these values right here. The big question we should start asking ourselves now is, will we be able to list all values? And as I'm pointing out this question right here, then apparently the question here is no. And the simple reason, we have an unlimited number of values. There are just way too much values out there, way too many values existing out there in the population to list. But again, we have to have a probability distribution. Any random variable must have a probability distribution. So really the biggest challenge now is how can we represent that probability distribution. So the idea of using a table to represent the probability distribution of our random variable fails here when we are working with continuous random variable, and all due to that fact that we are having an unlimited number of values. And so we have to make a note of that. Probability distribution. can no longer, and I have to make capitalized this term here, can no longer be represented by a table. So it becomes a crisis because we definitely need to have a probability distribution. But on the other hand, we cannot use table any longer simply because table will fail. We can never construct a table that's long enough to cover all values out there of our continuous random variable. But once again, the idea of the table is all about listing values and showing probability, high and low probabilities. And so now when we're actually working with continuous random variable where we're having an unlimited number of values, then to overcome with this crisis right here, to overcome with that situation about we can no longer represent probability distribution with a table, but we still need to have a probability distribution. Then instead of using table to represent our values, instead of using table to represent our probability distribution, we are using instead of table, so instead of table, we are using a what's so-called probability density curve. Okay. Probability density curve. And for short, a lot of time I and many other stat instructors tend to call this a PDC right here. So we are using a probability density curve to represent the probability distribution of our random variable capital X. So there's a whole world about what to understand of a probability density curve. And so, but our class here that we're learning is only an introductory level in statistics. So allow me to find what I believe to be the easiest way to understand what a probability density curve is. And so here's what to easily understand about a PDC right here, probability density curve. So remind yourself again, as I just explained, using table fails. So x equals 5, x equals 6, but we can have x equals 5.5, we can have x equals 5.1, and x equals 5.01. And there are a lot of values. So think about it. These values, if we put them all on a line, think about the idea of using a graph here. Then if we put a line like this, a continuous line like this, then it has all values that we can put. 5 could be here, and then maybe the 6 here is a 5 could be here, and 6 here is an interval, and then in between that we can have infinitely many values. And so the whole idea of probability distribution in a table back then is that we can show high probability or low probabilities, or high probability or low probabilities on any of these discrete particular values. But so that idea, similarly, when we bring that over and being brought into a PDC, then our PDC curves to become like this. There's high probability, there's low probability, high probability, low probability. And that's the idea of what a probability density curve is all about. So it's the curve itself right here is aiming at to represent the probability at one instance of value, of one particular value. Let's say here is a 5.2 right here, and this how high right here is about the probability. This height right here is about how much probability when your random variable equals to particularly 5.2. And that whole curve right here is actually is what we call the probability density curve. So this right here is a PDDC, probability density curve. But then, as I said, in our class right here, we're only an introductory level class in statistics. So the good news for us here, we don't even have to find, and once again, once you are looking at a curve like this, then anyone who is viewing this video is going to start thinking about, is there a function in terms of x that create this curve? Yes, there is, but it's not for our class. So if any of you eventually have a good passion for statistics and decide to go on and pursue an advanced career in statistics and must take a higher advanced stats level at a university level, then there they will teach you, you will be taught how to come up with those functions that represent your probability distribution. But here we only understand in its briefest meaning that the idea of using a PDC curve is to replace the idea of using table for a probability distribution. So this is a probability distribution for discrete random variable, and this PDC is the probability distribution for a continuous random variable. All right, and so now our comparison chart here can grow a little further. So as we just saw throughout the investigations, then all due to the fact that the discrete random variable is having a limited number of values, then consequently, or as a consequence, then a probability distribution can be represented as a table. And we saw all that explanation in my previous part of the video. But then immediately that feature, and we must have to have a probability distribution. But now that same probability distribution, if we're trying to display that in our world of continuous random variable, then here's the consequence that being continuous random variable brought to us right here. Any probability distribution in a continuous random variable, of course, can no longer be represented as a table. And then I had discussed earlier that we're gonna need to overcome with this situation, with this crisis right here, because we definitely need to find a way to display our probability distribution, because any random variable has a probability distribution. So we are using, instead of a table, we are using a what's so-called probability density curve. And a lot of time, like I said in my explanation, I use the PDC shorthand writing for that. To represent a probability. Distribution. And now for a discrete random variable. And particularly, let's look back at that example again on the Wheel of Fortune example, where we define a random variable x as the outcome, as money amount of each game. Then recall that on the probability distribution of this random variable from our Wheel of Fortune game, then the sum of probabilities, as we have learned and as I have pointed out, adding up all these probability entries must equal 1. So the sum of probabilities equals 1. And we already agree that in that way, one requirement to be any probability distribution, one requirement for any probability distribution of a random variable must meet is that the sum of all probabilities must equal 1. And we can quickly double check that adding up all these probability entries right here will give us a sum equal 1. And so now in a continuous, when we're working with a continuous random variable where we already knew that any continuous random variable has an unlimited number of values, and as a quick example that we have been following along, then let's look at the random variable x here to represent the height of a person. Then we also have learned earlier that the probability distribution of a random variable, of a continuous random variable, can no longer be a table as we have seen back in discrete random variable, but instead we must use, or we must replace, a table by what's so-called a PDC. And so now this PDC right here, this probability density curve, is to represent the picture of the probability distribution of a continuous random variable. And so the horizontal line here is again to represent from low to high. From low to high on the left to the right is where we can see all different values, various values of our random variable x being a continuous random variable. But now back to what I was saying. So currently we're talking about the sum. So being a probability distribution, the number one requirement is that the probability distribution that we're looking at must meet the requirements that sum of all probabilities equal 1. But then here we cannot see individual distinct probability entries as the case back in the discrete random variable any longer. And so in that case right here, here's the connection. The sum of probabilities, as we have seen earlier, this is one fundamental concept, the sum of probabilities. Now in the concept of a continuous random variable where we already replaced the table to represent probability distribution with a PDC, probability density curve, then the sum of probabilities here equals the area shaded inside the PDC. And so what do I mean by the area shaded inside the PDC? So now here's our PDC for a continuous random variable, any continuous random variable. And do not get me wrong that the PDC is only this short from whatever value here to whatever value there. It could be even infinitely long, but doesn't matter how far your PDC extends. The total area shaded inside, that's what I'm looking at. The total area shaded inside the PDC here is the representation of the sum of all probabilities. And so now in that way of our understanding, then as we have already agreed, the sum of probabilities on any probability distribution, because now in a continuous random variable, the probability distribution must be drawn as a PDC. And we just now learned that the sum of probabilities of a continuous random variable is represented as the area shaded, the total area shaded inside of a PDC. And so that means this sum of probabilities, we already knew it's always equals 1. And that means now back in the picture here, this total amount of shaded area has to be 1 or 100%. Okay, so this is 1 right here or 100%. Two different ways of understanding that, but that must be equal to the total area inside the PDC of any continuous random variable. And so now back to the growing side-by-side comparison chart that I was growing to compare directly the features between discrete random variable and continuous random variable. Then we can draw out another conclusion to be summarized here, to be compared here, that the sum of probabilities and then that is translated, that is equivalent to, is the same as, so let me get it a little more clear, the sum of probabilities in the table. In the table of probability distribution. So that sum of probabilities in the table of probability distribution is now the same as the total area shaded inside the PDC. And so that's how things are being at the same time connected. So the probability as a table is for a discrete random variable, and so that same probability as a table must be replaced by a PDC to represent the probability distribution. And then the sum of all probabilities in a table of probability distribution is now replaced by the total area, represented by the total area that's shaded inside the PDC, as I have demonstrated earlier. And so further, we have also learned that when the sum of probabilities back in discrete random variable, when we learned that the sum of probabilities of all probabilities must equal 1, then equivalently in the version when we're working with a continuous random variable, then the total shaded area inside the PDC must equal 1 as well. And that was again illustrated graphically in the picture I've had. And now when we're working with a discrete random variable, then this question was entirely possible to answer back then throughout our examples. Let's say we want to find the probability that our random variable equals precisely a value. Let's say back in this particular Wheel of Fortune example, then we were able to answer this question. Find the probability that our random variable equals exactly $100. And that answer was straight out from the table. 2 out of 8 as a probability, or 1/4. So we were able to obtain an answer to this kind of question right here, when our random variable equals a value specifically. Or now, generally speaking, for discrete random variable, we are able to answer the question as following. Find the probability where our random variable equals precisely a given value. So now I'm saying that this question is possible to answer. All right. Because we have, it's all due to the fact that we have a limited number of values in discrete random variable. So we can consequently list or display values discretely on a table of values like this, and along the way we're listing out the probabilities. And that's the reason why consequently we can find the probability, when we can easily find the probability where our random variable specifically takes a value. And that's why I'm saying this question here is possible to answer, meaning we can find an answer. And the way to find the answer, needless to say, comes right out from reading the table. But now think about if we are working with a continuous random variable where there are unlimited number of values. There's an unlimited number of values. And for as a quick example that we've been following along, let x is to represent the height of a person. Then can we do the similar thing as in discrete random variable? Meaning, can I ask such question? Find the probability where throughout the entire population we find a person that is exactly 5.5 feet. And I'm talking about exactly 5.5 feet. Now, we have to understand, I am not saying that the answer doesn't exist. I'm not saying so. But now I have to say, this kind of question is impossible. We won't be able to find an answer. So I'm not, and again, don't get me wrong, I'm not saying that this probability does not have an answer. It's just not for us to be able to find. So this is, and at least at our level of this class that we're currently learning, it is impossible to find the answer. And for the reason being, we just simply have way too many values. We have an unlimited number of values here. So it is impossible for us at our level is to be able to find the answer for this question. And so consequently, if it is impossible for us here at this level to find such answer, even though it still exists out there, then we're going to have to say that we must, this kind of question, okay, must be ignored. We are not doing this kind of question here in our particular statistics level that we're learning right now. So this type of question must be ignored. And so generally speaking, when we're working with a continuous random variable, the kind of question that find the probability where our random variable takes a value specifically equals a, or takes a value precisely equals a, some value, then this kind of question must be ignored. We can't answer that question at our level of learning. And so that is another good piece of information to put down in our growing comparison chart here. For discrete random variable, the question that finds the probability where our random variable falls precisely at one value is entirely possible to do. It's entirely possible to answer. But if this same question being addressed when we're working with a continuous random variable, then we must be sadly ignoring it. So this question here must be ignored, simply because we have way too much data, simply because we have a an infinite, an unlimited number of values involved. So it's impossible for us at this level to answer this question here on a PDC. All right, and now for a discrete random variable, when we were working with a discrete random variable, we were also able to do the following kind of problem. Find the probability where, let's say in this particular example, where we want our random variable takes value inside an interval, let's say anywhere from $0 to $100. Okay, so what I see now is that this is a probability question where we want our random variable finding the chance where our random variable takes value inside a given interval. And to do this with a discrete random variable where probability distribution is displayed as a table, then we can just simply add all values starting with x equals 0, x equals 100, x equals 10 is still inside of the interval, and including x equals 100. And so the answer here is 1/8 when x equals 0 plus 3/8 when x equals 10 plus another 2/8 when x equals 100. And we get the answer. 6 out of 8, or a 3/4. And so fundamentally the idea now is that for discrete random variable, we were able to find the answer to the question where probability of that a random variable takes value inside an interval. And so generally speaking, when we were working with a discrete random variable with probability distribution displayed as a table like this, then the kind of question where our random variable find the probability where our random variable takes value inside a given interval can be done by simply summing the probabilities, just like how I showed in a quick example, the probabilities from A to B. This is the beginning and this is the end of our interval. And so now when we are working with a continuous random variable, gladly we can also answer the same kind of question. Now keep in mind again, recall again that our probability distribution can no longer be displayed as a table, but instead we must display that we must represent a probability distribution as a PDC or using a PDC. That's why a lot of time I draw a nice smooth curve. It doesn't have to be anything special. It can be just a curve with up and down representing probability up, probability down, probability up, and probability down. And on the horizontal axis right here is where we place all values from low to high, from the left to the right of our current random variable x right here. So now let's say A is a value and B is another value, all among the different values of our random variable. Then the question that was addressed earlier, and let's say for this particular demonstration, let's look at the height of a person to be represented as the random variable capital X, then we can also answer this question. So what's the probability where the height of a person, that's what we are currently using in this current example. So what's the chance in the population that the height of a person is anywhere from 5.5 feet to 6 feet, for example. And so again, this is an interval of values, and we can think about, see, in the beginning here it could be a 5.5 around A point at the beginning of the interval, and 6 could be here. And so now this kind of question, finding the probability where our random variable in general take values between or inside an interval, is now very possible to be done in the world of continuous random variable when we're working with continuous random variable. Right now it is a little early to show other techniques to calculate, so I can only point out the idea that, so now the probability where our random variable, our continuous random variable takes value inside an interval can be represented by the shaded area. So on this picture of our PDC, this probability is represented by the shaded area inside the PDC again, but now between the interval. So, and at this point, as I said earlier, I am not yet able to point out specifically how we can find that area, but we will learn at a point later in our learning. So all anyone needs to know at this point is that this kind of question is what we actually can answer. And generally speaking, when we're working with continuous random variable, the question that we're finding the probability where our random variable takes value inside an interval is indeed, first of all, how about let me put it this way, is equal to the area shaded from A to B inside the PDC. So that's generally the way how we can answer this question. And further, I have to emphasize here, even though I did not emphasize for discrete random variable, but since we're working with continuous random variable and we already took away the kind of problem where we find a probability that our random variable equals exactly a value, this is currently not possible for us to answer. So as I said earlier, we ignore this kind of problem. And so now when we are in continuous random variable, we particularly always focus on this kind of question right here. So this kind of question is what we can answer, as I said earlier, and this is also what we always focus to. All right, so now back to the comparison chart that we were still growing. Then again, formulating the idea for a discrete random variable, we can answer the question. We can also answer the kind of question that find the probability where our random variable takes value either between or inside an interval. And finding this answer is simply done by summing the probabilities from on our distribution, probability distribution from A to B, from A to B. But now when we're working with this kind of question in our continuous random variable, again finding the probability where our random variable takes value inside an interval, then the way of doing this is to find the answer to this question equals the shaded area from A to B inside the PDC. But I also emphasized earlier that this kind of question is what we can do and what we focus. And the reason we focus on this kind of problem a lot is because we already ignore this kind of problem, as I said earlier. And so now any PDC that represents a probability distribution of a continuous random variable can create one of the following distribution shapes. Sometimes the PDC can create a distribution shape that has a one high peak focused area on the low end of the values and getting faded away to the right hand side. This distribution shape created by a PDC like this is called a skewed right distribution. And just like that, there are some other times a PDC can create the shape of the distribution to look as following, where the peak is formed in the higher end of the values. So we have, as a rule now, low to high from the left to the right of our random variable. Low to high from the left to the right of the random variable. And so a distribution shape like this, where we have a focused big area on the higher end of the values, this is referred as the skewed left distribution. And so what to remember about a skewed right distribution or a skewed left distribution is where the long tail that's fading away is pointing to. So in a skewed right distribution, the long tail indicating data fading away is extending to the right hand side, whereas for a skewed left distribution, the long tail indicating that data is fading away is extended to the left hand. And any one of these two either skewed right or skewed left distributions right here is being generally regarded as a skewed distribution. So these are the two quick examples of the skewed distribution. Skewed distribution shapes that's created by a PDC. And then among the shapes, there are times where the PDC formulates a picture where we can clearly recognize a center in the middle, or a center in the middle can be clearly recognized. And as usual, the random variable x is to be placed on the horizontal axis here. And when I say clear center, I mean for anyone looking at the shape, you can recognize there's a clear center, and the shape itself overall can be equally divided into two halves, and that's what it means by having a clear, recognizable center. And so in this case, a distribution like this is being regarded as a symmetric distribution. Another shape that's created by a PDC. And as a matter of fact, symmetric distribution is more as a family of distribution shapes where, again, as I said, there is a clearly recognized center, in a sense that we can recognize some symmetry in our distribution. So here I would put plural, because now among all of the symmetric distributions, or among all of the symmetric distribution shapes, there is one that's happening quite often in our stat work, that when data is symmetric again, but form into a one nice peak, and the peak is located exactly right in the middle. And so this is now famously, and we have seen that before in our quarter, this distribution shape right here, but now keep in mind it's being created by a PDC. It came out from a PDC, and the left and right on this horizontal line right here is where we can find all different values of the random variable, continuous random variable, capital X. And so a PDC that gives the distribution shape looking like this, a one nice peak in the center, and two sides are equally fading away. This is regarded as specifically a normal distribution. And so what to keep in mind now is that a normal distribution is one member in the entire big family of all symmetric distributions. So these are all symmetric distribution, and the normal distribution is the one that's a one member inside of that family. But now, starting at this point in our learning, then I can tell anyone that we will spend most of our time to study the distribution shape that is a normal distribution, because this is gladly the way how data happens most of the times. And outside of those that I briefly mentioned, which happen to be the common distribution shapes, there are still many other distribution shapes out there that unknown to any of us. There are other distribution shapes outside of those that we mentioned here, that they can become anything outside of those that we mentioned.